I have a 6-year-old and a 4-year-old. No, they don't have phones.
So I'm thinking that I got one in middle school, but it feels like every elementary school has.
Yeah, no. Thankfully, we haven't like had to think about that yet. It won't. It won't be for quite some time. Like, do I want to be able to track my kid? Yeah. But do I want him to be able to talk to people?
Track them with like a watch.
Yeah. The watch thing we would probably do. But you got a phone in middle school?
Yeah.
That that feels early to me. Like driving is when I got a phone, but it was like I was the youngest, and so my siblings had phones before me, and that was tough.
I started riding the bus, and my dad was like, "You need a phone."
Yeah.
I was middle school. I was homeschooled, so I didn't get it till I could buy it. So I was 16 after I worked at Dunkin' Donuts.
And you're stronger for it. All making all those gross sugar drinks. Okay. We are on page 10 of this note packet. We are finishing up equivalence relations today. And we'll probably start finite state automata today. So, fun all around. So we're in the middle of this proof, the proof of this theorem that these three statements are equivalent. So we proved the first two. This up here, this first part is the first proof, and then like this in between, and then this is 3. So we proved that I implies I already, and we have proven that I implies I. So now we're going to prove that this thing implies this. Are we on board? Yes? All right, so now assume for A, B, and A that the equivalence class of A intersects with the equivalence class of B is not the empty set. So then there's something in it, right? So there exists an X in that intersection. So X is in the equivalence class of A, and X is in the equivalence class of B because it's in that intersection, so it's in both. Exists. X is in A and X is in B. Thus, X is related to A and X is related to B. We're trying to show this up here that A is related to B. How shall we go about that? R is an equivalence relation. So it is reflexive and symmetric and transitive.
Can you make it symmetric and then say it's transitive?
Yeah. Yeah, so we can flip these by symmetry and then use the transitive property to have A is related to B. By symmetry, A is related to X, and by transitivity, A is related to B. We have shown I implies II implies III, and III implies Oh, wait, therefore, sorry, no box. Thus, the statements are equivalent. This is where I fell asleep at home, and I'm about to fall asleep now, too. And then I took a nap. And then my son decided to jump at the top of the stairs, and I thought he was falling down the stairs, and it woke me up in quite a startle. And he said, oh, oh. Mm-hmm. He went like this, right on the top of the stairs. You know why he did that? Because Ryan had just walked past him and said, your mom is sleeping, so be quiet.
I was going to say he knows what he's doing.
He 100% knows what he's doing. Okay, so this theorem gives us, oh golly, we can't see it. We'll go back to this theorem. This theorem tells us that either the two equivalence classes are completely the same or completely different. Yeah? So either they intersect everywhere or they intersect nowhere. Yeah? Okay, so either the equivalence classes are the same or their intersection is empty. This is, no, you're fine. Oh, sure. Yes. You know you can watch it in Teams. But you still could. It doesn't disappear. Yes. So this, okay. Pause. The equivalence classes form a partition of the set. So a partition is a union of disjoint sets that together make up the whole set. So a partition is just what it sounds like. It's a division of the things, but into things that don't overlap. So like the evens and the odds are a partition of the integers. Negatives and non-negatives are partitions of it's a partition of the integers because you got two disjoint subsets whose union is the whole set. Disjoint subsets whose union is the whole set, yeah. So equivalence classes form a partition of the set also, which is kind of cool. To get a feel for that, we're going to skip ahead a couple of pages. We'll come back to this in a minute, but we're going to skip ahead a little. Page 14. So we're going to talk about, so this is mod congruence, and we'll do more with that in just a minute, but I just want to talk about with remainders because we can do this without the mod stuff. We can just think about remainders. But mod arithmetic, or like adding or subtracting mod 5 or whatever, it partitions the integers because they go into these equivalence classes. Everything in this equivalence class of 0 is going to have a remainder of 0 mod 5. So it's going to be multiples of 5. So when we do this, like I'm just going to, so this is integers A with a remainder of R. So a remainder of 0 mod 5. So that I'm going to go like negative 15, negative 10, negative 5, 0, 5, 10, 15, and so on. Okay, so what kinds of things would have a remainder of 1 mod 5? Yeah, 1, 6, 11, 16, negative 4, negative 9, negative 14. What about a remainder of 2 mod 5? 2, 7, 12, 17. Negative 3, negative 8, negative 13. What about a remainder of 3 mod 5? Negative 2, negative 7, negative 12. and a remainder of 4 mod 5. Okay, so you notice what's happening here. Start counting. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Yeah? Yeah. Negative 15, negative 14, negative 13, negative 12, negative 11, negative 10, 9, 8, 7. See, they're all here. Every integer is going to fall into one of these things, right? So this is the equivalence class of 0, which is equal to the equivalence class of 5, which is equal to the equivalence class of negative 10, or whatever, right? These are all the same. This is the equivalence class of 1, which is the same as the equivalence class of negative 9, etc. Are you with me?
Yes.
So these things are disjoint. That means they don't have any overlap. But the union of all of them would give you all of the integers. So the equivalence classes partition the set. Everything will go into one equivalence class at most, and that's how that goes. So this is what's called a cyclic group. This is a cyclic group of order 5 because there are 5 things there. So like this is Z5. These are also generators of the cyclic group. Those of you who are going on to take abstract algebra, this will come back for you. So Z5 is from the remainders mod 5. So 0, 1, 2, 3, and 4. Z7 is the remainders mod 7, so 0 through 6. Z10 is the remainders mod 10, so 0 through 9, and so on. We will come back to this in a minute, but do you get the equivalence class situation and what that means with partitions? Yes? Okay. So let's go back up to where we are on page 11 now. Now we're going to talk about congruence mod D. So M and N are integers, D is a positive integer, M is equivalent to N mod D, and we write M is congruent to N mod D if and only if D divides M minus N. Symbolically, M is congruent to N mod D if and only if D divides M minus N. That makes sense, right? If the N is the remainder, right, mod D, so M minus N would make that number divisible by D because you're taking off the remainder. Does that make sense? Yes? Okay, so we would like to determine if these things are true or false, that 12 is congruent to 7 mod 5. So what we said before was that they have the same remainder mod 5, and that's true here, right? But you can also say, yeah, like 5 divides 12 minus, draw straight lines when you're supposed to draw straight lines. 5 divide 12 minus 7. Yeah, it does. So this is fine because 12 minus 7 is 5. On this one, does 4 divide 6 minus a negative 8? Oh, I don't think so either. That is 14, which is not divisible by 4. And then on this last one, does 7 divide 3 minus 3? Yes, it does. So we're good to go. Okay. So we're going to show that this means the same thing as them having the same remainder mod n. So that A is congruent to B mod m if and only if A mod m equals B mod n. We're going to do that now. This is an if and only if statement. So if we were trying to prove this from scratch, we would prove it forward and then backwards, right? So prove if then and then the other way. I'm going to do these as a series of if and only if statements because the the proofs are too similar to write it down twice. It's just the same steps backwards, and it's all definitions, so we're just going to go for it. You good? And if you want to see it broken up, I can. So we are going to let A and B and Z, and M and Z plus. Okay. Okay, then A is congruent to B mod M if and only if, by the definition up at the top of the page, if and only if M divides A minus B. Further, M divides A minus B if and only if what is true? What does that mean by definition? What does this mean just by itself? It's A minus B is equal to M times K, right? Oh, that's not a pen anymore. If and only if A minus B equals M times K for some K and Z. Oh no! I'm looking at the wrong proof. I was like, oh, my conclusion doesn't match what I was trying to prove because I'm doing the wrong proof. This proof is much longer. And it uses the quotient remainder theorem. I was like, something doesn't feel good. It's that. It's this. This doesn't feel good. Well, are you using a pencil today? That's good. Erase maybe all but that first sentence. Sorry, Michael. We'll prove that in a minute. Yikes. I'm sorry. I was like, where am I going? No, I'm not going anywhere helpful. Okay, so sorry. We got to use quotient remainder theorem. So we're going to do this in two. We are going to do this in two parts, which is why we have so much space to do it. Or maybe it's so that I could mess up and Michael could still continue on his way. Okay, so we are going to do this in two parts. We're going to go this way first. We are going to first assume A is congruent to B mod M. Wow, I'm so sorry. Oof. What are we trying to show here? I got to just make sure that I know what I'm trying to show. If I had done scratchwork tonight, that would have never happened. What am I trying to show here? That A mod M equals B mod M? So I want to show that they have the same remainder mod M, and that's how we're going to use quotient remainder theorem to do it. All right, so with this thing, I am going to say, well, by definition, bless you, I think. By definition, M divides A minus B. And we have A minus B equals M times K for some K in Z. Then A equals MK plus B. Okay, so we're going to use the quotient remainder theorem to rewrite B. So that's the like dr plus q. No, dq plus r. The r is the remainder. Do you remember this? Let's see, when was that? Was that in here or in 2? Whoa, it has been a long time ago. Test 1 notes? 2, test 2 maybe? I don't know, let's see. Oh, this feels like the right unit of notes. Hey, if y'all see it, holler at me. I notice I'm not actually looking at anything anymore. You're gonna go back to the beginning. Hey! 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 There it is. Okay, quotient remainder theorem. N is integer, D is positive integer. Then there are unique integers, Q and R. That R is trapped between 0 and D, where N equals DQ plus R. If it's divisible by N, then the remainder is 0. Or by D. Yes. Okay. So, oops, nope, don't want to be there. Okay. So we're going to use the quotient remainder theorem. There are integers Q and R such that B equals M times Q plus R. If it's divisible by M, then R would be 0, right? And if it's not, then R will carry whatever that remainder is. Yeah. It'll be Q times divisible by M. And R is going to be between 0 and M. So this means that B mod M is R, whatever R is. Okay, we have A is equal to MK plus B. And now we know that B is MQ plus R. So A is M times K plus Q plus R. Thus, A mod M is also R. So A mod M is equal to R, which is equal to B mod M. Now that feels really like not real to me. We've just made it be so, but it works. There's some remainder on that B. If the whole B is that remainder, that's fine. Okay, so we are going to then start with that. So we're going to go this other way. So we're going to assume A mod M is equal to B mod M. And what we want to show here is that A is congruent to B mod M, or that M divides A minus B. Okay, because these have the same remainder mod M, A is going to equal M times Q1 plus R, and B is going to be M times Q2 plus R. We don't know what those quotients are. We do know the M and the R are the same, but we don't know what the Q1 and Q2 are. All right, so then A minus B is MQ1 plus R minus MQ2 minus R, which is M times Q1 minus Q2. And then since Q1 minus Q2 is an integer, M divides A minus B, and thus A is congruent to B mod M. How are we doing with that? Do we grasp what's going on?
Yes.
I think I do now too. All right, questions or comments about that one? Your quietness is because you get it, or because you don't get it, or because you're tired, or because you don't know.
I get it.
Oh, you
Yes.
I like that you got every answer.
Yes. Okay. All right. Let's keep going. On this one, we are finding integers A that will fit these scenarios. And then we're going to talk through what that means for theorem 2. And that's the proof I tried to do a few minutes ago. So you already have a heads up on that one. All right, so we want to find an integer A such that A is congruent to negative 15 mod 27, and A is between 26 and 0. Negative 26 and 0, sorry about that. So I want a number that has a remainder of negative 15 and is between negative 26 and 0 when I do mod 27.
Remainder of negative 15.
The same remainder, sorry, maybe I should say that differently. The same remainder as negative 15 mod 27. That's fair.
Negative.
What is that?
It's my AirPods. They make noise.
Oh, they're dying. Oh.
They might be out. Alan's
They're just gonna keep going in your bag.
I think they think they're getting stolen.
Oh.
Every time. I'm just thinking through that. Are you stealing them from yourself? For myself? Yeah. They're cracked right now.
It's -15. Why?
Because it's not bigger than 27 or -27.
Because -15 is the number that's in that window.
Yeah.
I think I'll do better.
-15 is the one that's in that window. Now, if I wanted to have the same remainder of mod 27 as -15, Sherrod, how would you get the next one? Yeah, you can just add or subtract 27s, right? Add or subtract multiples of 27 and you'll be in the same spot mod 27, right? Because you're moving, think about coterminal angles, right? Like 30 degrees is the same as, I can't add, 390, right? Because you've moved a whole circle, a whole rotation, right? A whole rotation here is 27 units. Yeah? So you're moving a full rotation from -15 or whatever to the next one. You could add or subtract full rotations. So add or subtract 27. Emily's not convinced, but she'll get it on the next one. This is A is equal to -15. On this one, we want to be congruent to 99 mod 41, and I want my number to be between 100 and 140. It's not 139, it's 140, yeah. Why is it 140? You're going to do 99 plus 44. 41 is what I meant. 44. 99 plus a full cycle of the mods, right? So 99 plus 41 is 140. If you wanted another one, you would add 41 again to the next one, would be 181. So A is 140 here. What is that remainder mod 41? Since Jen and I forgot what mods are, let's talk about it. What is 99 mod 41? That wouldn't make sense. Keep going then. It's the remainder when you divide by 41. So that's 82, right? 82, 99 minus 82 is 17. So mod 41, 99 is equal to 17. So would 140 be, apparently. Yeah. Somebody figure out what 41 times 3 is 123. 140 minus 123 is 17. So these remainders are 17 mod 41. Ta-da. Emily, you know I'm going to pick on you now. So mostly it's because of the face you're making. So I would like to have a value that's congruent to 24 mod 31 and is between -15 and +15. So for the mod thing, I can move by this much, and that's the same as not moving at all as far as the mod goes. So I can do 24 minus 31 to make this number smaller. Oh, I think that's 7. Yeah, let's do it. So what is the remainder mod 31 of 24. It is 24. That was not very helpful. The 99 example is the best one. That remainder is 17. So you're going to keep moving. You want to find more numbers that have a remainder of 17, mod 41. Emily, are you good?
So I mean -7 mod 31.
It's 24. Yeah. Because the closest, how,
Be negative 31, it would be plus 24.
huh?
Because it would be -7, so you do 31 times -1, so you get negative 31. Then you plus 24 to get the 7.
Oh, and the quotient remainder theorem is what you're talking about.
Yeah.
Yes. Yes. I didn't get that, but yes. Because the mod stuff is the closest, how far are you from the closest multiple? And so those are going to be positive numbers. But that is the closest to negative 31. But it's 24 from negative 31. Math. Woo! It's 24 from, yes, we say negative 7 is 31 times -1 plus 24. Yes, or the D.
Yeah.
Q, the Q. Strange, weird, but yes. Good. I like it. The mod things are going to be positive because it's how far you are from the closest multiple, so you're always going to answer that with positive, whatever. Cool. -15 mod 27 is 12. Okay. All right, now this is the proof I tried to do earlier, but now we're ready. So m is a positive integer, a and b are congruent if and only if there's an integer k such that a equals b plus k times m. I actually was done with this proof earlier when I erased it, so that's really kind of a bummer. We're going to let a and b be integers and m a positive integer. You can only do mod with the positive integer behind the thingy. Okay, then A is congruent to B mod M if and only if M divides A minus B, but M divides A minus B if and only if there is some K in Z such that A minus B equals M times K. Thus, A is equal to MK plus B. I mean, this follows from the def. I mean, this is duh. This is a duh kind of a thing. A is congruent to B mod M. That's if M divides their difference, and if M divides their difference, then you can write the difference as M times K. So, yeah. Any questions about that proof or that theorem? No. 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 It's a shame to waste all this space, huh? Play tic-tac-toe. Who would win? Nobody. Okay, we are gonna prove, we're gonna show, we're gonna scratch work this thing, that congruence mod M is an equivalence relation. What does it mean to be an equivalence relation? It is, we're gonna start with reflexive because I get confused. We're gonna start with reflexive and then do symmetric and then do the transitive property, yes? Hi, Eunice. Welcome. Okay, so we're saying that A is related to B if and only if A is congruent to B mod M. This is the relation we're trying to show is an equivalence relation. We're on page 13, Eunice. Okay, so for the reflexive property, I want to let A be an integer. And I want to know, is A always congruent to itself mod M? How would I know? What's the definition of congruence mod M? M divides A minus A. Does M divide A minus A? Yep. So A is related to A. All right, symmetry. We are going to let A and B be in Z. We're going to assume A is congruent to B mod M. We want to show that B is congruent to A mod M. Why are they arguing next door? Oh, it's after class. Somebody has stayed after class to argue with him about something. Was something controversial? Who is it? Is it one of the engineering kids? Stop now. Maybe they heard us talking about
If they did, and these walls are really thin.
it. Yeah, they are kind of thin. Oh, Eunice, I would like to know what happened in there. Also, I didn't realize that Justin was in that class until I saw him walking out of there the other day. Does he speak in class?
I'm not sure who Justin is.
No. He's always eating an apple, probably. Wears a hat every day.
Guys with fancy deadline.
He is my age.
Oh, yes, I know him. But he doesn't come all the time. I think he has
Right.
the same thing as me. He's another class.
Oh.
And he also works.
Okay. Okay, we want to show that B is congruent to A mod M. What do we know from the fact that A is congruent to B mod M? Oh, I should turn off the front lights. I'll do that while you're thinking about what the definition of congruence mod M is. It's the same thing I've asked you 17 times. What does it mean to be congruent mod M?
M,
Divides what?
B minus,
No.
A minus B.
Yes.
Top one.
Top one. that M divides A minus B. What does that mean? Very good. What are we trying to show again?
B equals A minus
And what does that mean?
M divides B minus A.
Good. How are we going to get there?
With the A and B, and it's just minus.
That was kind of a weird way to tell me the answer, but yes. Maybe it wasn't. Was it normal?
I don't know. I've never answered this problem.
Okay. So like Brian said, you flip that order, it's going to make the other side negative because you multiply everything by -1. So you've got M divides B minus A, and therefore B is related to A. Are we all square? Yes? The transitive property. What do we have?
A, B, is it C?
Sure. We're going to let A, B, and C be in Z. What are we going to do with those, Michael?
Assume A congruence B mod M.
A is congruent to B mod M.
We also assume B congruence A mod M.
C mod M.
Show A congruence C mod M.
Good. All right. How am I going to get there?
You just kind of get what you did in the symmetric one.
What does it mean for A to be congruent to B mod M?
And divides.
Thank you, Michael. I was really like, oh no.
I can read that part. I was like, if only it was written somewhere like multiple times.
Right. M divides A minus B. What else do we know? M divides B minus C. What do those give us?
A minus B equals M. B minus C.
Good. I like it. Okay. What are we trying to get? What does it mean for A to be congruent to C mod M?
M divides.
Michael, you're not allowed to answer it anymore because I believe that you know it. I'm not convinced everybody else does. M divides A minus C. Good. Okay. How do we do this? Oh gosh. Yep. Congruent to C mod M. Questions or comments or concerns? No? All right. What else we got? Nothing. Okay, let's go. What do you think happens to sums and products under mod? Yeah, huh? I don't know. What do you mean? Well, if I know that, like, I don't know, 5 is congruent to 2 mod 3, and I also know that 4 is congruent to 1 mod 3, what happens if I multiply? What happens if I multiply 5 and 4 mod 3? what is the remainder when you multiply mod 3? Like, what's 20 mod 3? It's 2. You multiply the stuff on the left, and you multiply the stuff on the right. Fascinating, right?
Yeah.
So when you multiply these, you get 20 and 3. Oh, that's a 2, you doofus. We'll add in a minute. No, we won't. Am I supposed to be adding now? I don't know. We're multiplying first. It does say sums and products. Whatever. We'll do products first. This is still true, and it's just multiplication, and that's pretty cool.
Use another example that doesn't have one.
Yes. Can we use 5 still? How about we use another 5? Good.
Yeah.
Other questions about products under mod? You multiply the remainders too, which is kind of good. All right, for sums, if we do the same one, so 5 is congruent to 2 mod 3. Sorry, I kind of already did this and spoiled it for you, but whatever. If you add, what is 9 congruent to mod 3? It's 0, yeah. So you can add these, and then fix this. So 9 is congruent to 0 mod 3. You've just like increased the Q by 1. Yes,
So
Michael.
the middle one can be 25 equivalent to 1 mod 3? Or is it just?
Oh, yeah, sorry, my bad.
Okay.
Yeah. I was thinking to 21, but yeah, you're right. 24 is also fine. Yeah, because that's,
Oh,
yeah, right. Okay. Questions or comments about that? This is true all the time, which is nice, and we're going to prove that now. So if A is congruent to B mod M and C is congruent to D mod M, then what happens when we add A and C? What do we have on the other side? We have A is congruent to B mod M, C is congruent to D mod M. What would A plus C be congruent to? B plus D mod M. And A times C would be congruent to what? B times D mod M. Yep. All right. So we're going to do this. You ready? Yes, we are going to let M be an element in Z plus and A, B, C, and D be integers. We're going to assume A is congruent to B mod M and C is congruent to D mod M. Oops, that just says D mom. Okay, so what do we know from those two things? No, Michael. Yes, of course. Please. A minus B. Keep going.
Keep
Mhm.
going. So then A minus B equals MK and C minus D equals ML for some integers K.
I'm still just so shook that you would have chosen political science over doing math or computer science when this seems to like work for you.
You should see me talk about politics. At home, I was crazy. They hated me at Thanksgiving. They didn't like to see me coming.
Do they now?
Oh, that was just, like,
You should
I
talk
don't
about
mean
proofs.
hate. I'm just saying, like the.
Now you can do proofs. That's
Yeah.
true.
Yeah.
Who wants to learn about
I'm
induction?
gonna be talking about proofs.
Induction. Can you get on the ladder? I don't know. Let's figure it out.
My mom told me my cousin needs help with chemistry.
Oh no. Run! Run! Okay. A minus B is M times K, and C minus D is M times L for some integers K and L. Good, Janaya, I'm good with that. Would you guys like to... So first we want to show for this one that M divides that their difference, so A plus C minus B plus D. So I'm going to add those two equations together. Does that work for you? We have A minus B plus C minus D is equal to MK plus ML. I'm going to rearrange this stuff. This is A plus C minus B minus D is equal to MK plus M. I'm just going to go ahead and do this. K plus L over here. But then I can throw in some parentheses and things are all right with the world. Well, here in this class right now. Since K plus L is an integer, M divides A plus C minus B plus D. And we have A plus C is congruent to B plus D mod M. All right, now we're going to say remember or recall A is equal to MK plus B and C is equal to ML plus D. Thus, A times C, because over here we're trying to show that M divides AC minus BD. So A times C is going to be MK plus B times ML plus D. That's M squared KL. Ugh. MKD. It's a lot of letters. MLB, hey, baseball. MBD. So we have AC minus BD is equal to M times MKL plus KD plus LB. So M divides AC minus BD, and we have AC is congruent to BD mod M. Questions or comments? All right. We already did this, Eunice, earlier. Sorry. I skipped ahead to do that a little while ago. So these are our cyclic groups of order 5, 7, 10. These things are cycling through. We did the equivalence classes earlier. This is just what happens with mod stuff. Addition and multiplication mod M satisfy almost all the same properties of ordinary addition and multiplication. It's closed under addition and multiplication. So if A plus B, if A and B are in here, then A plus B mod M is in here. I don't know. This is fine. The answers to these things are in the set. That's what it means to be closed under addition. You add two things in the set, you get another thing in the set. To be closed under multiplication, you multiply two things in the set, you get another thing in the set. So under mod, they're closed. These groups are closed. And then finding an additive identity means you can left add or right add and you get zero. I mean, you get the same thing back. That's what it means to be an additive identity. An additive inverse, you add left or right add and you get zero. So it's like in regular addition, it's the negative, right? So A and negative A. Multiplicative inverse, find something to multiply by so that you get 1. This is interesting in these groups because, you know, it's not like the fraction, right? If we're in the real numbers, a multiplicative inverse is the reciprocal of your number, right? So, yeah. But when we are in these things, they don't always have to have multiplicative inverses, and we're going to talk about an example where there isn't one in just a second. So in Z7, so what does Z7 look like? This is the set of remainders mod 7. So what does Z7 look like?
0 through 6.
Yeah, it is 0 through 6. The additive inverse of 4 is 3, because 4 plus 3 is 7, and 7 is congruent to 0 mod 7. That's kind of trippy and weird, but you're looking for the thing to add to get you back to 0. In Z7, the multiplicative inverse of 5 is 3, because 5 times 3 is 15, and 15 is congruent to 1 mod 7. Because 14 is 1 off, right? Okay. So we are going to work in Z6. What's Z6?
0.
0 to 5. We're going to show that 4 has no multiplicative inverse. So we want to try to multiply 4 by everything in here and see if we can get 1 mod 7. 6, I mean, sorry. So 4 times 0 is 4. It's not. Even in mod, it's not. It's 0, which is congruent to 0 mod 6. 4 times 1 is 4 now. And that's congruent to 4 mod 6. We okay so far? 4 times 2 is 8, which is congruent to 2 mod 6. Tracking? Yes. 4 times 3 is 12, which is congruent to 0 mod 6. 4 times 4 is 16, which is congruent to 4 mod 6. And then 4 times 5 is 20, which is congruent to 2 mod 6. So we tested 4 with every element in the set. We did not get a remainder of 1 mod 6, so it has no multiplicative inverse inside of Z6. We are okay with that? Yeah?
Yep.
Let's look at Z10, and we're going to find the additive and multiplicative inverses of 7. So what's Z10 look like? I want to know 7 plus something is equivalent to 0 mod 10. It is 3. Woo! So that's its additive inverse. It makes it 0 back out. Are we okay with that? What is the additive inverse of, I don't know, 6? Yeah, it is 4. Good. All right. And 6. We're not going to do that probably for multiplicative, but we'll look at it. So we want to know 7 times something is congruent to 1 mod 10. It is 3 because that's 21, and 21 is congruent to 1 mod 10. Is that okay or not okay? Yeah? Additive, multiplicative inverses of 7. Has to be something inside that set. Yep. So like 6 times 0, 6 times 1, 6 times 2, 6 times 3, 6 times 4, 6 times 5, 6 times 6, 6 times 7, 6 times 8. I'm tired of writing. 6 times 9. 6 times 0 is 0. That's not going to be congruent to 1. 6 times 1 is 6. That's not going to work. 6 times 2 is 12. We are mod 10, so that's going to be 2. 6 times 3 is 18. That's going to be 8 mod 10. 6 times 4 is 24. That's 4 mod 10. We're looking for a remainder of 1. That's 30. That's not going to work. That's 36. That's not going to work. That's 42. That's not going to work. That is 48. I can add. That's not going to work. That is 54. That's also not going to work. Okay. When will an element, first, when will an element not have an additive inverse? It will always have an additive inverse. If you are looking at, and you're in Zn, say, you have X in Zn, the additive inverse is n minus X, because that'll add up to n, which would be congruent to 0, mod n. Yeah? Oh, I was supposed to use an M. I just didn't do that at all. How about not having a multiplicative inverse?
Your examples, you had 2 even numbers and you're trying to get an odd number.
Yep. You can't do it if your number is not relatively prime with the thing you're going for. If you want to know X's multiplicative inverse, it has none if the GCD of X and M is not 1. I could say this in a way that wasn't so negative. Has 1 if the GCD of X and M is 1. If they are relatively prime, then it will have a multiplicative inverse. Are we okay with that?
Yeah.
Okay. That is because the remainders are going to move by whatever that smallest common divisor is. No, not the least one. Greatest one. It's going to move by that many. See, there is a gap of 2 in all of these remainders. We go from 0 to 2 to 4. We're not going to get any odd numbers because those have the GCD is 2, not 1, right? So we can't move by 1. Okay. I am not going to start 12.1 because we're out of time. So you guys have a great rest of your day. Homework 12 is going to be due on Wednesday. Homework 13, I'm in the process of writing. It is over 12.1 and 2 those, so we have some time. Okay? All righty. Y'all have a great week. Hang in there. Drink lots of water. Eat oranges. Stay healthy. Vitamin C, Janaya.
Yeah.
Get some vitamin D also. Enjoy the sunshine. Sunshine. All righty. Goodbye.